All right.
Right. So I think we should be live at this point. All right. Yes, I think we are.
All right. So thank you for coming to our talk tonight. Mark's going to give us a great talk. This is our Faces of Physics speaker series, and we want to give a shout out and thanks to a few people before we get started. Marshall University, the College of Science, the Physics Department, the American Institute of Physics, West Virginia Space Grant Consortium, they've all helped financially sponsor this speaker series. So we're very thankful for that, and we're thankful for Marshall University and the College of Science and Physics Department for supporting our SPS group here at Marshall. Always very supportive and helpful for anything that we do here in the Society of Physics students. And special thanks to Jackie Seisman. So they deserve a big round of applause, and they've done a fantastic job with it. Ellie all the way up until the end here, and she's going to convince the next SPS members to continue this. So I really appreciate all the effort that she's done for this. If you're interested in some of the things that you hear about, definitely email our speaker, strike up more of a conversation with him. You can try to email us here in the physics department if you're interested in taking physics courses here at Marshall. We have about 10 faculties, 6 that are active in research. We have 5 degree paths with areas of emphasis in applied physics, biophysics, medical physics, medical imaging. So if any of those are interesting to you, let us know. Yeah. Questions, let us know. I will get you. It is around 9,400 undergrad students and about 2,800 graduate students. It is an R2 doctoral university. So we do have a BS and an MS degree in the physics department in physics. So reach out to us if you have any questions about those degree programs, and I will be happy to get you the information that you need. So I look forward to hearing you talk, and I'm going to pass you off to Ellie White, and she is going to properly introduce our speaker. So thank you.
All right, thanks very much, Dr. McBride. Really appreciate it. So first of all, thank you all so much to everybody who's out there joining us. So this will actually be the 10th talk in our Faces of Physics series. And I'm really excited to hear our speaker tell us about his work relating to the technology that's used in radio astronomy and the search for extraterrestrial intelligence. I'm sure all of you are excited for that too. So I'll be introducing him very soon, but first just a few quick points to cover. So after the presentation, just like all the other talks in the past, if you were here, you'll remember that we will have a question and answer session at the end. We welcome you to share your questions via the YouTube live chat, or you can post your questions on Twitter by tagging us with @MUPhysicsClub. If you enjoy this presentation, we hope you'll join us for future talks in this series. Our next speaker and our final speaker this semester will be given by MU Physics graduate Emily Sutherland on the 2nd of December at 7 p.m. Eastern. More information about this talk will be announced soon. If you'd like to receive email updates about upcoming events, we'll be sharing a link in the YouTube description where you can go to sign up. Finally, if you missed any of our past events, please head over to our YouTube channel page and check out the recordings. Now it's my pleasure to introduce our speaker, Dr. Mark Ruzindana. Dr. Ruzindana received his BS, MS, and PhD degrees in electrical engineering from Brigham Young University in 2015, 2017, and 2021, respectively. He specializes in research and digital signal processing techniques for radio telescopes and related instruments. Currently, Dr. Ruzindana is a postdoctoral scholar in the search for extraterrestrial intelligence and the SETI Institute at the University of California Berkeley, and he is conducting research in digital signal processing techniques as well as software development with the Breakthrough Listen project in the SETI Institute. Dr. Ruzindana has also been involved in the installation of a fascinating project at the Green Bank Observatory called FLAG, which is essentially a radio camera that gives us a lot of pixels on the sky to look at neutral hydrogen, something astronomers are very interested in. So I was fortunate enough to meet Dr. Ruzindana when he and a group of colleagues were visiting the observatory to test FLAG on the Green Bank telescope. So he and his group actually invited my mom and I to come up to the control room and watch him test it. That was super kind of them and absolutely amazing thing to witness. So definitely a super cool example of science in action. So we are beyond lucky to have him join us this evening, and I'm delighted to pass things over to him right now. Thanks again to all of you for coming, and a huge thanks to Dr. Ruzindana for making the time to talk about his work with us in the midst of all the amazing work he's doing.
Thanks, Ellie. That was That was very kind of you. So I'm going to discuss digital signal processing techniques in radio astronomy and applications in SETI. It'll be more of a, hopefully it'll be a discussion that will kind of educate the general audience and so on the work that I'm doing. So if this goes, oh, there we go. All right. So a bit of an introduction into radio astronomy. So radio astronomy is the study of radio sources in deep space. The signals that we receive can be -20 to -50 dB below the noise floor. Some of these sources include pulsars, which are rapidly rotating neutron stars that radiate pulses, periodic pulses, fast radio bursts, which are currently being studied. They're kind of somewhat unknown phenomena that are being studied right now in astronomy, radio astronomy, and H1 galaxies, which are radiate electromagnetic or generate electromagnetic radiation due to a change in energy state of neutral hydrogen atoms, hence the name H1. That's neutral hydrogen. So just to give you a few images, or provide you with a few images on what's observed with radio astronomy or radio telescopes. We have on the left here the M87 black hole that was, this image was generated with the Event Horizon Telescope, which is a group of telescopes around the world that enabled or that generated this particular image. Then in the middle here, these are gas jet structures from Cygnus A that were generated by the VLA, the Very Large Array in New Mexico, and on the right is Cassiopeia A, also from the Very Large Array in New Mexico. So these were images that were generated by radio telescopes. Some examples of radio telescopes are, these are the instruments that are used to detect or to receive signals from deep space. So some examples of these radio telescopes include the Effelsberg telescope in Germany, which used to be the world's largest fully steerable telescope with 100 meters in diameter. The 500 meter aperture spherical telescope in China, or FAST. And there are other radio telescopes that are interferometers, such as the VLA, which I just discussed, the Very Large Array in New Mexico, which is a set of antennas that are approximately tens of meters in diameter. And then the Meerkat array in South Africa, the ATA, the Allen Telescope Array in California. I'll discuss the Meerkat array later on in the presentation, because that's specifically what I'm working on, or that's I'm currently developing software for that telescope with a work project that I'm working on. So this is the Green Bank telescope, which is the world's largest fully steerable radio telescope, 100 meters in diameter, but it's not completely circular. So the other dimension is 110 meters, I believe. It's located at the Green Bank Observatory in West Virginia. This is where the focal L-band array for the Green Bank telescope was deployed. It's the instrument that I primarily worked on during grad school, along with another project for the Office of Naval Research that I'll discuss briefly in this presentation. And the instrument's placed at I'm not sure if you can see my cursor, but it's placed at the feed of the telescope right there. Okay, so just a brief description of what phased array feeds are. So a phased array feed is a 2D planar array that's placed at the focal plane, or the focal point of a large reflector dish that spatially samples the focal plane. So, an example of a path would be FLAG, which I discussed in the previous slide. These paths are typically used to form multiple simultaneous beams over a field of view, which is referred to as beamforming. So the process of beamforming, so essentially, the sample voltages from each element sample voltages are received by each element The sample voltages in this case in the diagram are represented with the x sub index of n. So x sub 0 through x sub p minus 1. That minus is not great. Yeah, so the sample voltages are received by each element and then multiplied by a complex weight coefficient. The complex weight coefficient points the beam. So you can think of a beam as a pixel on the sky, essentially. So it points the beam in a particular direction. And this product is so the product between the sample voltages and the weight coefficients are summed to form a beam in a given direction, theta. So as the diagram shows. Yeah. Just to give you a brief introduction to calibration. So with all of the instruments that I've worked on and that I know of, there's always some sort of calibration procedure for most of these instruments. Sometimes they're slightly different depending on what the instrument is. For PAFs, for FLAG in particular, we performed calibration on a bright source. Typically, the source was called 3C295 that we performed calibration on regularly. So we perform calibration on the bright source. We take on pointings, which are essentially pointings on source, and then off pointings, which are pointings off source that will give us an estimate of the noise environment. So the figure shows an example of a kind of scan, or one of the scans that we regularly used, mostly used when conducting observations with FLAG. So it's called a raster scan, and you pretty much just move the telescope across the bright source, and then you point off source to get the off pointings to get an estimate of the noise environment. So with those two data sets, you can pretty much detect those very weak signals that I discussed earlier. So using various techniques. Don't worry too much if you don't know what eigenvalue decomposition is. So it's a technique that we use to estimate the vector that would enable us to point in any given direction. So we would get a dominant eigenvalue. That dominant eigenvalue would represent the most powerful signal within that environment, and then get the vector corresponding to that eigenvalue. And that vector would enable us to point in any given direction, and any given direction within the field of view. Then with that steering vector, we're able to generate coefficients, the weight coefficients that I talked about earlier. The equation that is on the second bullet is just an example of a technique used to maximize the signal to noise ratio. The R is just a covariance matrix, which is a matrix containing element. It contains, each element within the matrix contains relative power between the elements of the array, and all of these, essentially, these measurements, the covariance matrices, just enable us to characterize the performance of the array, and also improve help us develop different kinds of beamforming techniques and so on. So in this case, the max SNR beamforming technique. So essentially the on pointings, and the takeaway from this is the on pointings would have the signal plus the noise, and then the off pointings would just have the noise. And with both those data sets, you would be able to detect the signal in question. So like you would be able to increase the signal to noise ratio so you could actually see these signals that are very, very weak. Okay, so moving on to the actual instrument that I worked on. So again, it was the focal L band array feed for the Greenback telescope. L band is approximately 1 to 2 gigahertz, between the 1 to 2 gigahertz band. There were 19 dual, this is the array on the right here. There were 19 dual polarization elements. Polarization referring to the orientation of the so when the waves are propagating towards the array, they're oriented in a particular way. So one polarization would be perpendicular to the other. So we'd have an X and Y polarization, and the X polarization would be perpendicular to the Y polarization. So effectively, we would have 38 elements, effectively. Yeah, so 19 dual polarization elements. The front end analog bandwidth was approximately 300 megahertz compared to an instantaneous signal processing bandwidth of 150 megahertz. So the array itself had a bandwidth of approximately 300 megahertz, but the backend, the digital backend, processed only 150 megahertz of the 300. So it processed the center of the band, essentially. So actually, not necessarily the center, depending on where the LO was, where the center frequency, where you set the center frequency. And I'll discuss this more in the next slide. So yeah, so just to provide you with system architecture. So this system architecture is pretty much, one way or another, is very, very similar to what most radio telescopes tend to have. Yeah, so essentially, you have a front end and a digital back end. In the case of the Green Bank telescope, the front end was miles away from the actual back end, which was in the Jansky lab, if you're familiar with that at the Green Bank Observatory. So yeah, so just a brief description of the system architecture. So you have the front end, which has 38. So it has 38 elements, 38 connected elements, 2 of which were disconnected because there were only 38 in the array. And then you have low noise, cryogenically cooled low noise amplifiers, digital down converters that mix the signal down depending on what the LO is set to. And then the signals are transported over optical fiber to the digital backend. These Roach 2 FPGA boards essentially did channelization. So they decomposed the signal into its frequency components. So yeah, they essentially just converted the signal from a continuous signal in time to discrete frequency components, discrete frequency channels. So in the case for FLAG, it decomposed the signal into 500 frequency channels. And then these 500 frequency channels were distributed over 5 HPCs, or high performance computers, using this Ethernet switch. And then this Ethernet, these HPCs are primarily where I worked. This is essentially where I developed the software to do real-time processing as well as post-processing and so on. So yeah, so essentially you can effectively think of the Roach 2 boards, or the FPGA boards, channelizing the data, and then the HPCs processing fractions of the total bandwidth, that 150 megahertz bandwidth that I discussed earlier. Yeah, okay. So yeah, so within each HPC, within each HPC, real-time digital signal processing was performed. So such as the beamforming that I discussed earlier, as well as correlation. So those covariance matrix that I discussed earlier, those were generated in real time as well. And that was all done with the help of HASPipe. And HASPipe stands for the High Availability Shared Pipeline Engine. And it's a real-time operating system that pipelines tasks into separate threads with semaphore-controlled shared memory buffers in between each thread. The semaphore-controlled shared memory buffers are essentially just, the semaphore-controlled nature of it is just, it's a flag that you raise to 0 or 1. So 0 being these blocks are empty, and 1 being, oh, these blocks are full. And yeah, it's a real-time operating system that I used during both projects, FLAG, as well as the next project that I'll talk about with the Office of Naval Research. And I'm currently using it right now to process data in real time as well. So yeah, so the essential mechanism of it would be this first thread would be a sort of like packet capture thread. And then the second thread would be a processing thread. And then this third thread would be like a save thread that saves the data to some sort of files. Currently, with what I'm working on, there are only 2 threads, and the second thread does both. Essentially, it processes the data and saves the data to file. But yeah, different for Flag. Okay, a bit of a block diagram. Don't worry too much about the math. It's essentially just showing the processes that took place within for Flag. So there were 3 particular modes. There was the real-time beamformer, real-time correlator, coarse channel correlator, and then a fine channel correlator. And the coarse channel correlator just processed the data from the FPGA boards, directly from the FPGA boards without any further channelization. And then the fine channel correlator with this fine PFB block further channelized the data. So you could effectively think of it as just zooming into a fraction of the bandwidth, another fraction of the bandwidth. So we use this fine channel correlator specifically to map for H1 galaxy mapping. So yeah, that's primarily what we use this fine channel correlator for. And then, yeah, so the data is processed and then saved to FITS files, which are files commonly used by radio astronomers for recording their data. And then, yeah, they were all stored to disk in this Luster disk array storage. Okay, so with Flag, we did quite a bit of testing with it. We went out to Green Bank, I believe 2 or 3 times, and then worked remotely and acquired data remotely as well. The next few slides show some data that we acquired, as well as some figures of merit. This particular slide shows sensitivity maps. Sensitivity being, you could think of it as a sort of scaled signal to noise ratio that, again, helps to characterize the performance of the array. So the left image shows a sensitivity map in the X polarization, and then the right image shows the sensitivity map in the Y polarization. The Y polarization during the observations that I was part of had malfunctioning elements. That's why it looks distorted. But essentially, this just shows sensitivity across the entire field of view of the array. And this data was acquired using that raster scan that I talked about earlier by scanning a bright source, in this case, again, 3C295. So yeah. So with this data, we were also able to calculate or generate beams. The beams shown in this particular slide were the beams used in the real-time beamformer. So we would calculate the sensitivity, calculate these beamformer weights, and then plot them to make sure they look as they should. And in this case, again, on the left, we have the X polarization and the Y polarization. Each of these images is the entire field of view. So if you look at these, at the X and Y axes, you have negative 0.2 to 0.2, which is similar to the images on this slide, negative 0.2 to 0.2. So yeah, so they show the entire field of view, and we would select particular beams within that field of view and use those beams for the real-time beamformer, which primarily was used for detection of transient sources or observation of transient sources such as pulsars, and also trying to detect fast radio bursts, which I don't think we were fortunate enough to detect. So another figure of merit is the system noise temperature, which at the time, I haven't looked into this, but at the time, Flag had the lowest recorded system noise temperature of any instrument, of any phased array feed, which was about approximately 24 Kelvin. The figure on the left just shows the instantaneous signal processing bandwidth. with a center frequency of about 1.45 gigahertz. And then the plot on the right shows the full analog processing bandwidth. And the way that we got these images on the right, or these curves on the right, was by shifting the LO. So we would scan at a particular frequency and then shift the LO by about 100 megahertz, and then scan again, and then continually get data across the entire band. So we got data during May of 2017, August of 2017, and February of 2018, as well as, and we compared them against these models. The GPT-2 model, which was developed by a student at BYU called Junming Jiao, and the GBL model, which was developed by NRAO. So yeah, so we compared them against those two models, which they roughly follow the curves of the estimated T-SIS. And you can see the observations in February of 2018 was when we recorded that extremely low system noise temperature. Yeah. And then with this, and then we also were able to detect pulsars. This is just an example of one of the pulsars that we were able to detect with the real-time beamformer. It's a known pulsar, B2011 plus 38. And you don't really have to worry about the rest of the images to the right. Just focus on the time series plots. You can see the pulses, the two pulses on these left images here. Okay, and then we also have, we're also able to map H1 Galaxies, an example of which is NGC 4258, and also generate spectral plot, and it's clearly an H1 Galaxy because they they resonate at approximately 1.418 gigahertz. Yeah. So yeah, that was FLAG. I worked on it quite a bit, I think approximately 3 or so years. That was just a brief summary of the kind of work that I was doing there. And then I moved on to develop a wireless communication system for the Office of Naval Research, very similar to the radio telescopes that I worked on and I'm working on right now. The only difference is that it was designed to detect wireless communication. It was designed for wireless communication. So this is the system here on the left. I'll show a system architecture which will show the similarities in a little bit, but it just had a 16 element patch array, a 4x4 square patch array with some analog to digital converter cards and a bunch of other stuff. At the bottom here are the HPCs that we used for processing. And then on the right, we used, initially we just used a function generator connected to an antenna to transmit just a pure tone, just for simple testing. And later on, we used a software-defined radio to transmit audio signals to actually test to see whether we could actually detect the signal with the raw voltage mode, as well as other techniques that I'll discuss later on. Okay, so very similar structure to FLAG, much smaller. So we have that front end with the LNA, down mixing, signal gets transported over to the back end. The FPGA boards in this case were different. They were snap boards. And then again, the data is evenly distributed across HPCs. In this case, there were only 3 HPCs that we used for processing. And yeah, further processing was done. And then the demodulation, at least when I was working on it, was done in post-processing. So yeah. Similar block diagram to what we had before, except this time it's just showing the XRFI mode. The XRFI stands for the RFI mitigation. So it's a play on, it's canceling RFI, so XRFI. So the real-time beamformer and the real-time correlator operated the same way. Those two modes operated pretty much the same way as flag, but this particular mode also had the addition of correlation, as well as generating what's called a projection matrix. This projection matrix would then be applied to the weights that we discussed earlier, and those weights would be applied to the beamformer. And this subspace projection technique would be used to mitigate RFI, in the case of the Office of Naval Research, it would mitigate RFI in hostile RFI-rich environments. So in environments where there was RFI trying to jam the signals that they were using to communicate. But in the case of radio astronomy, which hopefully this would be adapted to, it would be used to mitigate RFI, which is a very big problem in radio astronomy currently. So this is just a block diagram showing the inner workings of that piece of software. So then just discussing the RFI mitigation algorithm development a little bit further. This subspace projection algorithm was implemented on GPUs similar to the other algorithms. I think I neglected to mention that, but so all these algorithms that I've discussed were implemented on graphics processing units, which speed up computation quite a bit as compared to just processing them on a CPU, on a central processing unit. So in this case, the RFI mitigation algorithm was tested with simulated data as well as real data, as I'll discuss later on. But in this case, just to show that it was working, we simulated some RFI, just a pure tone, in the side lobe of a particular of a beam, of one of the beams, and the plot on the left will shows the output of the beamformer with no subspace projection, and then the one on the right shows the beamformer with subspace projection. So effectively, all it does is it places a null, a very deep null, in the direction of the RFI, as you can see on the right. So, and the null that's placed in the side lobe has to be very deep, given that since the signals can be the signals of interest can be very low below the noise floor, you would want the null to be as deep as it possibly can be, so you can mitigate RFI that could possibly also be below the noise floor. So, yeah. We conducted other beamforming experiments in post-processing with a raw voltage mode that did no further processing in real time. So we just got raw voltage data. So we used numerous techniques just to compare against conjugate field match beamformer, which just maximizes the gain of the signal. So that's the blue curve. So you can see that the blue curve just has, so in this case, the signal of interest was a pure tone and the RFI was a frequency modulated tone. That was, I think, around 200 kilohertz wide. And you can see that with the next output or the next technique, which was with the equal weights, where the weights were just set to 1. So it's effectively just summing across the elements. So yeah, with that, you can just see the full FM signal. It doesn't really, that particular beamformer doesn't really do anything to mitigate the RFI. And then we used the subspace projection technique to get the dominant. Essentially, it also utilizes the technique that I discussed earlier, the eigenvalue decomposition, to get the dominant eigenvalue and then to get the corresponding eigenvector, and use that to mitigate the RFI. So this is all assumed that the RFI is significantly stronger than the signal of interest. And then the second technique that we used just to see if we could was to mitigate both signals using the subspace projection technique. So taking both dominant eigenvalues And so far it looked like all these techniques would be valid and will be tested in real time later on. We were able to test just the subspace projection technique on a single dominant eigenvector and compare it against just the real-time beamformer. So we just had pure tones. In this particular case, we had pure tones, one of which was the RFI, and then the other one was the signal of interest. This is very zoomed in, just for your information. This is additional channelization just to see, they would otherwise be overlapping in the same coarse channel. As you can see, the red curve represents the XRFI mode, and it mitigates the RFI with minimal or no distortion to the signal. And then the blue curve represents just the real-time beamformer with no RFI mitigation with the same exact setup, and you can clearly see the RFI. So we successfully were able to mitigate RFI in real time. And then we conducted further experiments with actual FM audio, and we were able to, I believe we were able to detect or to listen to the actual audio transmitted from the software-defined radios. And we just used two different signals. I think the signal of interest was someone speaking, and then the RFI was like the Cantina song from Star Wars, and it was always annoying when the Cantina song kept playing. Okay. I think that's pretty much, that pretty much sums up the work that I did with that wireless communication system with ONR. So then moving on to the current work, the work that I'm currently doing. So I currently am working on the Breakthrough Listen project at UC Berkeley at the SETI Institute. I'm specifically currently working on the Meerkat system. The goals for the Breakthrough Listen project, at least pertaining to Meerkat, are to study 100 galaxies, conduct a survey of the Milky Way galactic plane, and observe 1 million stars, each for approximately 5 minutes, for at least 5 minutes, in approximately 1.5 years, I think, from when we actually start observing with the system. So the image behind here is of the Meerkat array, where the cat in Meerkat stands for Karoo Array Telescope, and it's located in South Africa. Just some facts about Meerkat. It's a radio quiet reserve in South Africa. There are 64 Gregorian antennas, each 13.5 meters in diameter. I believe the longest baseline is 8 kilometers, and the shortest one is, I don't remember off the top of my head right now, but the longest baseline is 8 kilometers. I've worked with that one a little bit more. The bandwidth currently is 856 megahertz at L band, 544 megahertz at ultra high frequency or UHF. And I think they're also currently developing an S band, S band is between 2 to 4 gigahertz, I believe. And then at L band, the field of view is about 1 degree squared. To those that are not as familiar, 1 degree seems very small, but the signals that are of interest to us could be potentially like billions of light years away. So relatively speaking, it's actually quite large. We can discuss that later if you'd like. So some of the science goals, we intend to form 64 commensal beams. Commensal meaning we would be observing, or we would be acquiring data at the same time as the primary observer, all within the same field of view. So the field of view in this case, all these images and these slides, credit to Cherry Ng. She developed these slides, very, very descriptive and helpful. So the field of view is this green circle, and we intend to form 64 coherent beams, coherent meaning they would be phase aligned with a particular radio source or a star, as the brown patches show. And then the pink is just the primary observer, or would be the primary, would be the beam, the main beam within the center beam within the field of view. So the plan would be to choose 64 targets within from a 26 million star catalog derived from Gaia, which in itself is a star catalog. And we would be able to observe 64 of those. So essentially we would be observing 64 targets in real time with real-time coherent beamformer. The coherent beamformer is currently what I'm working on. And the timeline is hopefully I'll be able to get it to work by mid-January of next year. I think it's very doable. I currently have some results, but I didn't want to show the results without, I would need to go into more technical detail to show what I currently have. And more coming soon, more results coming soon, I guess. Just to show you a bit of or talk about the processing pipeline for Meerkat. Very similar to what I discussed earlier, bit of a simpler diagram. So we have the F engine. The F engine is pretty much those FPGA boards that I showed earlier in the previous system architecture diagrams. It essentially just does the channelization, as well as a few other things like quantization and so on. But the thing to focus on is the channelization. And in this case, there are 3 modes. And since we're doing things commensally with a primary observer controlling things, we don't really have control over what mode will be used. So we'll pretty much just have to adapt to whatever mode is selected. So each mode represents how many subchannels would be coming out of the F engine. And from there, we would do further channelization. Just to give you a perspective, the channelization that's going on here. So the frequencies or the subchannels from the second stage, in this case, are 1.59 hertz, which is very, very narrow, given that we're trying to detect technosignatures, and the technosignatures would be assumed to be quite narrow. And just for comparison, the previous systems that I worked on, or with FLAG, the second channelizer only reduced the subchannels down to 9.5 kilohertz. So this is very, very narrow. Okay, and then from there, we would do an incoherent sum, as well as calculate the 64 coherent beams. And then there would be a turbo SETI or a SETI search of some kind using machine learning that would help detect technosignatures, hopefully in real time. And so just to discuss what I'm currently working on a little bit further. So I'm currently working on that coherent beamformer, trying to optimize it to process the data in real time. Hopefully down the line, work on making the software compatible with most or all interferometers. Actually, right now, the goal is to have it be dynamic or compatible with the VLA, seeing as there's another project that we're working on called Cosmic, which is the commensal open source multi-mode interferometer cluster SETI. So it's very similar to the Meerkat project, but it's, rather than Meerkat, it's just at the VLA. And then possibly down the line, also maybe write some code to for an automated RFI mitigation software, and then hopefully detect some technosignatures with the software. So and then just some pictures from Green Bank, West Virginia. The one on the left is at the Green Bank telescope. The one in the middle is just me being silly. I made my other colleagues do the same kind of pictures. And then the one on the right here is with Mitchell Burnett and Richard Black. Mitchell Burnett is currently getting his PhD at BYU and is working on Alpaca, which is also another project similar to FLAG, or it's pretty much FLAG 2 at Green Bank. And Richard Black currently works at L3. Another picture of Mitchell Burnett at the Green Bank telescope next to the receivers. And this is us at the Jansky lab, I believe, at Green Bank, at the Green Bank Observatory. I think this is where Ellie saw us work. So yeah, that's it. Any questions?
That was so cool. Thank you so much for that.
Yeah.
Really amazing stuff that you're doing, and yeah, just thanks for going into detail about it. And yeah, I know I'm going to be coming back to this talk a lot as I try and learn more about phased arrays. So this is really cool. All right, so I'm going to pass it over now to Eli, who is going to man our questions. So we have some comments in the chat here. Eli, if you'd like to kind of read them off, and we can kind of encourage people to ask questions, post where they're from, just kind of share some stuff in the chat.
Yeah, so I've got 3 comments here right now. We've got 2 from Deanna White. The first one says, "That's pretty impressive." Definitely impressive work. I loved the talk. And she said, "This is an exciting project. Thank you for sharing the details on it."
Oh, thank you. Thank you. Yeah,
And
you're welcome. Sorry.
And then towards the end of the talk, we got another one from Erica Raskin saying, "Fascinating."
Oh, well, there you go. Thanks.
And we'll see if any more questions come in. See, I've got one here that I was just kind of thinking about while you were talking about the architectures.
Mm-hmm.
So you mentioned that they use NVIDIA GPUs, and I know that there's been a shortage of NVIDIA GPUs lately. How has that affected the architectures and such?
Yeah, it's delayed things quite a bit because just due to because they're all, even though they're currently they're trying to sell everyone GPUs, but they're so expensive. So everyone's kind of just waiting until the next year till we can actually buy some GPUs. So. Yeah,
because I know personally I use GPUs a lot in my computers because I play games on it, but I had been looking at some of the cheaper lower end GPUs, and even those are being scalped for high prices right now. So
yeah. Yeah. Yep.
Well, I'm not seeing any more questions coming in here. Oh, no, actually, we got one more from Deanna White. Says, "So the Meerkat project could potentially detect a technosignature in real time, allowing a verification from a different site in a timely manner."
Yes. That's that's pretty much it. Yeah.
Okay, and then we've got another question from Kaylee Burdett. It says, "What is your educational background? Physics, engineering, or both?"
It's in electrical engineering, specifically digital signal processing. Yeah. Hopefully I'll gain enough experience to somewhat call myself a physicist, kind of.
Yeah, and actually, guys, in the description of the live stream here, you can also see some of his information that Ellie has put in here. So we'll wait a little bit longer to see if any more questions come in, but right now I'm not seeing any.
All right, well, if there's no others in the chat, I have a couple. That's okay.
Yeah.
All right. So you showed that really cool plot of the kind of the flag beams on the sky, where you had kind of the contours surrounding the kind of the beams. So I was just curious, in terms of arc seconds or arc minutes, what are the size of those beams and how separated are they?
Oh, in terms of arc minutes, I believe there were about 0.3 arc. No, there were 9 arc minutes wide. And they were about 0.3 arc minutes separated, I believe, if they weren't overlapping. Sometimes I believe they were overlapping, but maybe at other points we separated them by about 0.3 arc minutes, I think. Yeah.
Okay, cool. So like with the beamforming stuff, you can kind of steer them so that they're kind of change the amount of separation. Is that kind of how that works?
Yeah. So with that raster scan that I talked about earlier, so we would get all of the steering vectors corresponding to the beams in that raster scan, and then just select a few of them that correspond to like any particular need. So the radio astronomer on hand would select specific beams, a specific orientation of beams from that grid. So
that's really cool.
Yeah.
Neat.
Yeah.
Okay. And the other thing was just, I was just saying yay because software-defined radios. I think there's several people probably watching that are kind of also fans of software-defined radios. I have several, so it's not really a question. But I did have one other actual question about the RFI mitigation. So that was really cool what you guys are doing with the kind of doing that in real time. It would definitely be cool to get something like that on the GPT. So
yeah, that's kind of the hope. Currently, so the other project I was talking about, Mitchell Burnett, my previous colleague, he's working on a project called Alpaca that will be on the Green Bank telescope, and I think they're going to try and move the software that I developed for the RFI mitigation into that project and kind of help in that area.
So the algorithms that you guys are using in terms of the kind of trying to get rid of the signal. So I've heard of different methods, like some people use like the kurtosis of the signal or things like that. Some people just kind of cut out RFI where they know it is. So what kind of technique are you all using in terms of deciding what is and what is not RFI?
Yeah, so we use the subspace projection technique, which essentially just you use an eigenvalue decomposition to determine what the dominant eigenvalue is in the subspace or in the environment. And in this case, it's assumed that the RFI would be significantly more powerful than the signal of interest. And that's always the case in radio astronomy, so that's not really a problem there. So, or at least for the most part, it's the case in radio astronomy. So so you'd get that dominant eigenvalue and then form what's called a projection matrix with that dominant with the vector corresponding to the dominant eigenvalue. And then using that projection matrix, you would apply that projection matrix to the weights, and then that would force the null in the direction of the RFI. But if the RFI is in the main lobe, then you're kind of toast. But yeah, as long as it's in the side lobes, then you're fine. Then you should be able to mitigate it.
Yeah, that makes sense. So I guess what I'm thinking of is a little bit different because I'm thinking of single pixel RFI mitigation. So it's kind of a different kind of setup. So that's really interesting.
Yeah. Mm-hmm. Yeah.
Okay. We've actually got 3 more chats, and the first one here is from Apostolos. I'm sorry if I'm butchering the pronunciation, but it says, "Thanks for the brilliant talk. I was wondering what makes a particular GPU card more appropriate than another GPU for DSP?"
So it all, at least in my experience, it all depends on what you're trying to do. So like, for the most part, I'm pretty sure most people wouldn't mind having a perfect GPU that has as much memory as it can have, and so on. But at the end of the day, it's just cost. So essentially, if you want to have like, if you have a certain amount of bandwidth and you're trying to process this bandwidth with a certain amount of nodes, the thing that limits you is just the amount of money that you have to buy. However many compute nodes you need or however many GPUs you need. So yeah, it just comes down to cost. That's pretty much it.
Yeah, that definitely boils back down to the GPU shortage that we were just talking about.
Yeah.
Okay, we got another one from Deanna White that says, "Thank you for this great talk. We enjoyed it and learned more about DSP and radio astronomy."
Oh, thank you. You're welcome.
And then we've got a question from Destiny Mac. It says, where is the biggest satellite?
The biggest satellite? So like the biggest, I'm assuming like the biggest reflector dish, I guess. Yeah.
That's all I'm working with.
Okay. I'm not sure about the satellite in particular, like if you're talking about like the devices that orbit in space. But in terms of the reflector dish, I believe it's the one that I showed earlier, the 500-meter aperture spherical telescope in China. So it's 500 meters in diameter. And then I think prior to that, it was Arecibo, but Arecibo's no longer there. So yeah.
Quite sad.
Yeah.
Okay. I'm not seeing any more chats coming in. So Ellie, if you want to take it away.
Yeah, sure. Well, just thank you again so much, Mark, for this absolutely fantastic talk, and just for making the time to be with us, and really appreciate it.
No problem. No problem at
Absolutely.
all.
Thank you for giving a great talk, and you've definitely built yourself up quite a resume in the community working on all these projects. I mean, that's really impressive that you've had your hands in so many of these projects. It's pretty impressive.
Thank you. I appreciate it.
Well, I guess I'll say goodnight for the evening and kind of stop the stream. So thank you all again so much for coming, and hope to see you next time.
Yeah, thank you. Thanks.